My name is Mikkel Peters, and this is Lab 1 for Physics 2111, Constant Velocity. In this report, I will cover the introduction and theory of relevant physical concepts, an overview of experimental procedure, and explanations for how the observational and computational data were collected. We will then compare the data and answer the lab questions, what if and what does it mean? The purpose of this lab was to apply Newton's second law to everyday life by observing an object at constant velocity, or at a constant speed without changing direction. Using Newton's second law, the goal was to analyze the results to determine if the surroundings were exerting a net force on the object, or system, which we will cover in the theory section. This was achieved by comparing the data from observation, analyzed by the program Tracker, to a computational model in GlowScript. As a preview of the results, this experiment was unsuccessful, as it did not produce the expected result of a constant velocity, but instead showed a changing velocity. Newton's second law, otherwise known as the momentum principle, states that the net force from the surroundings acting on a system can alter the momentum of a system over a given period of time. This means when the net force acting on the system is zero, the velocity is constant. This is demonstrated by the equation on the right. When F net is equal to zero, the final velocity is equal to the initial velocity over a given interval of time. It is important to note that the variables F, P, and V in these formulas are vectors, meaning they have both magnitude and direction. Before we begin, it is important to note that in this case, the system is the baseball and the surroundings are the air, floor, earth, and everything else the baseball may have come into contact with. I first filmed the baseball rolling across the floor at a constant speed. I then uploaded the video into Tracker to record the ball's position at each time interval. I then used GlowScript to create a computational model using the same initial conditions to predict the position of the ball over time. I then used Excel to create a plot showing the outcome of both observations and predictions on the same graph. I then analyzed the graph to compare the data. Once I uploaded my video to Tracker, I began tracking once the ball had fully entered the frame, ensuring a constant velocity. I calibrated Tracker using the average diameter of a baseball, 0.075 meters. I recorded the baseball in the center of the ball to remain consistent throughout each frame. The initial conditions for this scenario were an initial position of 4.57 times 10 to the negative 3 meters, an initial velocity of 0.364 meters per second, calculated by the change in position over the first time interval, and a frame rate of 30 frames per second. I then moved to my computational program in GlowScript. I changed the ball's initial position to approximately 4.5 times 10 to the negative 3, the velocity to 0.364, and the delta t to 1 over 30 for 30 frames per second. These changes were done to mimic the initial conditions of the observed data for a more accurate prediction. The graph on the left shows the position versus time for both the observed data and the computational model. As expected, the computational model in orange shows a linear slope with a constant velocity. Using Newton's second law, this suggests there is no net force acting on this system. However, the observed data in blue shows a changing slope that dips below the predicted line, meaning that the velocity is not constant. According to the momentum principle, this suggests that there is a net force acting on the system. Our data obtained from observation does not match the predictions of the momentum principle or the kinematics equation to the right, which demonstrates that zero net force results in linear changes in position over time. Although our two models are similar, our data did not match the computer's predictions, since the velocity was not constant. Therefore, there was a net force acting on the system of the baseball in this scenario, and the experiment was not successful. Sources of error could be friction and air resistance, or errors during the tracking input. Our what-if question asks us to consider how the results would or would not change if the axes were flipped. For this experiment, I chose to orient the axis of my graph so the ball will be traveling in the positive x direction. If the axis were flipped, the results of the experiment would remain the same, except the ball would now be traveling in the negative x direction. Since flipping or mirroring a vector does not change its magnitude, the only change in this scenario would be in the direction, which you can see by this graph of the unit vector formula, which is the vector divided by its magnitude. Our what does it mean question asks if we can determine the number of pushes and pulls that are acting on a system to give a net zero force. Our computational model does not have any forces acting on the ball, since it's an ideal model and not the real world. Therefore, we can't determine the amount of forces acting on the system. But for our observational data, we do experience a non-zero net force acting on the system, evidenced by changes in velocity. However, it would be impossible to determine all of these individual forces through observation alone.